this topic is based on this preprint with source collaborators. So the motivation of this talk is analysis of very higher order complicated networks. So in order to capture rich information that may be hidden in a complex networks that may contain the interaction beyond pairwise interactions. So the modeling of the data beyond the graph-based analysis will be crucial. For example, the graph analysis does not straightforwardly tell us more than the connectivity of the networks, so which is a very limited topological information. But more higher order dimensional topological information may be hidden in a complex data. So for example, nowadays there are many kinds of complex informations such as complex networks or the structure of protein or even the immunoscience. And the main object, the main way of modeling such a higher order networks in this talk is a simplicial complex, which is commonly used among such higher order networks studies. And simplicial complex is a collection of simplices. Simplices is a set of vertices, and that is closed under the operation of taking subsets. And the asimplex is said to be d-dimensional if it is composed of d+1 vertices. And the asimplicial complex is said to be d-dimensional if the maximal dimension of all simplices is d. And for example, a one-dimensional simplicial complex is a common graph, which is composed of vertices and edges. The vertices are zero-dimensional simplices, and the edges are one-dimensional simplices. And the two-dimensional simplices is a set of triangles and edges and vertices. And if you take the subset of triangles, which are the edges, they are also in the element of the simplicial complex. And if you consider three-dimensional things, which is the tetrahedron may be added. So you can imagine this kind of geometric picture. So those are the collections of tetrahedrons and triangles, edges, and vertices. And for example, the faces of tetrahedron, which are triangles, is also the element of the simplicial complex. Okay. And the particularly important class of simplicial complex in this talk is a clique complex. And the clique complex can be defined through a description of a graph. And the clique complex is a collection of cliques in a graph. And the K-cliques is a subgraph of the graph, which forms a K-vertex complete graphs. For example, one clique is just a point, and two cliques is a lines. This is three clique, and this is a four clique, and this is a five clique. So when you are given a graph, you can find the cliques, and you can consider those cliques as an element of the clique complex. So the nice property of clique complex is as follows. So although the number of cliques in the clique complex can be exponentially large in the number of vertices, then the clique complex can be succinctly described by only the description of the graph. So this is a very nice property of clique complex, which makes this clique complex practically relevant. And if you know about the independent sets of the graph, clique complex can be also thought about the independent sets of the complement of the graph.
Is it unique? So given a clique complex, is there only one graph that will give this clique complex? Or can I have multiple graphs giving me the same?
Yeah, graph is a description of the clique complex. So
okay, let's see.
Only one. So the edges are no.
Yeah, okay, yeah, no.
okay. Basically, I will talk about results on clique complexes. And so I want to highlight what is different in higher dimensions compared to the analysis in graphs. So I want to highlight with those perspectives. So first is the number of nodes. So for graphs, the number of nodes is the number of vertices, which is n. Or if you think about the edges as nodes, the number is of order n squared. But for simplicial complexes, the number of nodes is n choose k, which can be very large if k is not a constant. And for graphs, the vertices are connected by edges. So this means that vertices are connected by one-dimensional higher object of edges. But for simplicial complexes, there can be two different notions of adjacency. One is the upper adjacency, which can be analogous to the case of graph. So the k simplices may be connected by sharing a one-dimensional higher simplices. For example, those two lines, those edges share the same triangle. So those edges are upper adjacent. But you can also imagine a lower adjacency, so which means k-dimensional simplices, which is connected by k-1 dimensional simplices. So in this picture, so those two blue edges are connected by this vertex. So they are lower adjacent. But so those two blue edges are lower adjacent, but they are not upper adjacent because they do not share triangle.
I have a question. So there's two triangles here. They are also connected by a vertex. Would that be like a k-2 lower adjacency?
Yes. Yeah. So yeah, you can also imagine such a more than one-dimensional relationship, and you can also consider such a maybe. Yeah. But we talk about this kind of +1 or -1 dimension.
And
Yeah.
sorry, with the number of nodes, why is it n choose k and not, I don't know, the sum of all the possible n choose k? Is it just one level of the simplicial complex or all of the
Okay,
whole?
so yeah, this n choose k is just the maximum number of possible sorry, this should have been k+1 actually. If I'm looking about k simplices, so this should have been n choose k+1. So this is just the upper bound for the number of possible.
Of the top things?
Yeah,
Oh.
if you consider every dimension k and k-1 and k-2, and maybe you are correct. So you have to sum up all of them. But so here I'm just thinking that for example, just thinking about k dimension simplicity as nodes. So yeah, I just wanted to highlight that the number can be grown very large. So that's only that's the only. And for graphs, and there is no inherent orientation on vertices, but for simplices, there can be a different choice of orientation for simplices. So basically, we can assign a plus or minus orientation for k-dimensional simplices, but maybe we can consider more complicated orientation. Actually, more asymmetric orientation can also be considered, which is studied in the name of path complex. But we are just think about this plus-minus orientation. So I think those are the key differences that makes the study of simplicial complex different from that of graph, and makes it more complicated and maybe interesting.
So sorry, this orientation extends also to higher dimensions.
Yes.
Like for a tetrahedron, how do I think of it?
Yeah, maybe you can just maybe you are given an orientation in some way, and if this ordering of vertices is given to be a positive orientation, you imagine that the permutation of those vertices with even permutation has the same orientation. And
I see. So it's just the ordering of the zero-dimensional things, basically. Okay.
you said that the simplicial complex had an efficient, like a succinct description because you could specify by the graph, right?
Yeah.
How does it work if you add orientation in there?
So yeah, that is a different point, but yeah, maybe there can be several ways of giving orientations and considering giving. For example, so if you imagine the problem of choosing a good choice of orientation, this task itself can be very complicated because this may be related to the sign problem. So orientation can be considered as in some sense sign, but you can also consider a very straightforward choice of orientation. For example, if the vertices are ordered in an increasing order, you can assign that to be a positive one. So you can consider the orientation in your own way, but the choice of orientation does not matter the homology. So any orientation can be can work principally. So yeah.
I'm just new in those things. I just want to understand the difference between the simple complex and a directed graph. Because if I have a directed graph, I assume that it still has some orientations inside.
Yeah. Yes. So yeah, that is one way. So yeah, I think the simplicial complex of oriented graph is a very interesting topic, and it is studied on its own. And maybe you can, if you are interested, you can search the path homology. So path homology studies the homology of directed graphs. So maybe you can cover that if you are interested.
I don't think that was quite what he was asking.
Sorry.
But I think what he's saying is that these adjacencies between simplices, they come with signs depending on the orientation. And in a directed graph, they come with a direction.
Yes.
So if you had two different directions, you would get a sign. So it's like two orientations is equivalent to a signing. And here we have a signing.
Yes. So yeah. So basically, we have to consider those upper and lower adjacency and orientation. So then I want to, the topic of I want to talk about is homology. So I want to introduce what does I mean by homology. So let's consider a very simple one-dimensional case. So this cycle, those four edges forms the cycle, and this can be considered as a whole. But if you look at this blue cycle, this is also a cycle, but this is not considered to be a whole, because this cycle can be written as a boundary of triangles. So basically, we say that a cycle is a whole if it cannot be written as a sum of boundaries of one-dimensional higher objects. So this can be formulated in this way. So we can define a boundary operator that maps p-dimensional. This CP is a space spanned by p-dimensional simplices in a simplicial complex A. So this boundary operator maps CP to CP minus 1. And this is formally defined in this way. And then the homology group can be defined as the cotent space of the kernel of the boundary, this p-dimensional boundary operator, and the image of the p plus 1 dimensional boundary operator. And one nice property, one very important property of the boundary operator is that, so if you apply the boundary operator twice, it always goes to 0.
Sorry, what is the W of the I in this equation?
Sorry, yeah, I didn't mention about that, but this is some weight function assigned for the vertices. So we we are thinking about some weighted version of simplicial complexes, and we consider the weight of the simplex is given by the product of the weights assigned on vertices. So, and this is the weight of the vertex. But maybe you can ignore about that. So, yeah, maybe you can just imagine that this W1 is just 1. And then the p-dimensional Betti number is defined as the dimension of the p-dimensional homology group. And this Betti number represents the number of p-dimensional holes that exist in K. For example, if K is 0, beta K represents the number of connected components. And if K is 1, it represents the number of one-dimensional holes. And if K is 2, it represents somehow three-dimensional holes, and so on. Okay, so far I have talked about topological property of a single simplicial complex, but in topological in the topic called in topological data analysis, the persistence of holes in the family of simplicial complexes is considered. So now I am going to talk about the topology that varies in the sequence of simplicial complexes. So let me introduce about the typical pipeline that is used in topological data analysis. So we may start from some given data, which may be a point cloud, and there is some, and the distance of each point can be calculated, and the procedure of Beatrice, the so-called Beatrice filtration is as follows. So you first make a ball with this radius around those points, and if the balls intersect, you connect the points. So if you make a ball with this radius and those intersects, you connect this, and by connecting this, you obtain a graph, and you will include the cliques of this graph.
So, sorry, how do you pick the epsilon?
You can just choose. So yeah, this is a parameter that you can choose. So somehow you can just increase the radius of the balls.
Yeah, I think in the end, we're interested in what happens as we increase epsilon, right? We should see how things fill in.
Yeah. Of course, the good choice of radius may depend on the data, but we can change the radius and continue this procedure. And maybe if you make the radius very large, everything will be connected. So there will not be any holes. So, and you can make a family of simplicial complexes. And the persistent Betti number is a very important topological invariance in TDA. And the p-dimensional ij persistent Betti number is a number of p-dimensional holes that exist in this Ki that still exist in Kj. For example, in this example, if you look at the first Betti number between times 3 and 4, this is equal to 1, because you can imagine that this hole exists in time 3, and this hole still exists in time 4. But if you look at 2 and 4, in time 2, the hole does not exist, so the persistent Betti number is 0. And if you look at 3 and 5, the hole is filled by triangles, so the persistent Betti number is 0. So the topological data analysis is popularly used because they have some good properties. And one good property of TDA is the power of discriminating noisy holes and important holes. And we can think that topological invariants that persist longer in the procedure of filtration may be more important than that only exists very short terms. So for example, that we usually say that the topological donuts is a torus, but real world donuts may contain very noisy holes. This hole is a very important. That makes donuts not donuts, but there may be many more noisy holes. So we want to discriminate noisy holes from important holes. Yeah, but maybe these noisy holes may also affect the taste. So maybe this is also somehow we want to discriminate. So TDA offers a very nice systematic way discriminating noisy topological features from important topological features by combining both the geometric and topological methods. The geometric means, so in the previous picture, I introduced some geometric radius, so they combine geometry and topology in a wide way. And how in the behavior of topological invariants in the filtration is usually summarized in this kind of barcode. So yeah, so the main motivation, so we want to discriminate noisy holes from important holes.
Just to get a picture, important holes are like long persisting holes. And noisy
Yeah,
holes are
yeah,
things that
basically,
are
so yeah, of course, there may be important holes that persist very short time, but now I am assuming that long living hole may be important.
Okay.
So
Depends on the task.
yeah, of course, this is not made. This might be false in sometimes, but in general, we can imagine such a, we can see in such a way. So in those barcodes, yeah, so maybe there can be appearing holes in such a very in such areas, but maybe this hole might be more important. I'm sure. Okay, so as I have said that the number of simplicial complexes can be grow exponentially. So there have been several attempts to use quantum computing for the topological data analysis. The first attempt in such a direction is given by those authors, and they provided a quantum algorithm for estimating the normalized Betti numbers. Normalized Betti number is this quantity. So this is a p-dimensional Betti number, and this is a number of p-dimensional simplices in simplicial complex X. So the task is to estimate this normalized Betti number within an inverse polynomial additive error. And I also studied the quantum algorithm for I extended this previous results to the estimation of normalized persistent Betti numbers. So those quantum algorithms performs exponentially faster than the non-best classical algorithm for certain regimes. So this is very nice, but there are several I want to highlight two limitations in the previous studies for quantum topological data analysis. So one problem is the usefulness of normalized persistent Betti numbers. So because usually in classical topological data analysis, they almost always consider the non-normalized, just a usual persistent Betti number. So how the normalized persistent Betti number can be utilized is not so clear. And another problem is that for typical simplicial complexes, the normalized persistent Betti number tends to be exponentially small. This is also a problem. And so if you try to compute the persistent Betti number exactly, the problem is known to be sharply hard, so may not be solvable in general. And if you try to approximate the persistent Betti number within a multiplicative error, this is known to be QMA hard. So this problem may also not intractable for quantum computers.
So, I remember you estimated up to like +1/poly n.
Yes.
So if it's exponentially small, then you don't want to actually.
Yeah, does not make sense. Yeah, of course, there are some simplification complexes with exponentially large bit numbers. So it makes sense for such a complexes, but so the problem is that the quantity is tends to be in many cases. And the second limitation is so the evidence is about the evidence for the exponential speedup. Because no known complexity theoretic understanding of the normalized persistent bit number problem for practically relevant complexes has not been known, such as the grid complex or the Beatrice slips iterations. So the closest known result is the complexity of normalized bit number estimation for general simplicial complexities, or some generalized problem is known to be DQC1 hard. So, but we do not know this kind of hardness results for the grid complexes. So those are the two key limitations that exist that can be said for the previous studies of quantum TDA.
For these MDM complexes, is there an upper bound on it?
I think it is in DQP, but under some promises. So if the problem satisfies some problem such as some spectral gap of this kind of operator, this can be solved. Okay, then in this talk, so I want to introduce about our new problem in topological data analysis. So the main problem that we talk in this, I introduced in this talk is persistent problem that we call. So this problem can be informally introduced as follows. So imagine that you are given two simplicial complexes and the description of the dimensional holes in A1. And the task is to decide if the given hole persists in K2. So you are given some description, you are given some simplicial complex and the description of a hole. And the task is to decide if this hole persists in K2 or disappear. As I said, knowing if a hole persists in this filtration or die out is a very practically motivated problem in topological data analysis for discriminating noisy holes and important. One problem is that how can we represent the holes? So we have to consider about that to formulate the problem.
Sorry, so is it important here? So these K1, K2, they are completely arbitrary, or should they also come from increasing the epsilon of like some points in space?
Yeah, maybe the only constraint is that K1 is a subset of this.
So it's just graph theoretical subset.
But they all come from the same data, right?
If you assume that those complexes are constructed from a data.
But that's not, the data is not part of the problem. It's just only this inclusion sets.
Yeah. So yeah, actually it would be ideal to be able to show some results for filtration of a point cloud, but we have not able to show such a result.
We have a question online from Ronald. He says, I'm confused about how long persists formulation. Is there a time dimension here? Could you explain this again?
Yeah, so in this case, so the how long, I mean, in the sequence of filtrations. And in this picture, I am just concerning about if this hole is persists or does not persist. So in this picture, the meaning of how long is not included in this picture, but if you look at this kind of pictures, maybe there is many sequences of simplicial complexes, and the length of this bar can be considered as length of persistence.
Sorry, these simplicial complexes are obtained by incrementing the epsilon for the balls of interaction?
Yes.
But I think in this problem, they're not there.
They're not,
Yeah,
they're just
yeah.
arbitrary.
Yes. Yes, yeah, that's true. So, yeah, we are considering arbitrary inclusion of Cleve complex. Sorry, given what?
Like how are you given K1 and K2?
Yeah, so those are described by graphs. So you are given graph 1 and graph 2, and K1 is a Cleve complex of graph 1.
As like a adjacency matrix?
Yeah. But we need to give a description of the holes, but there can be actually many choices of possible representations of the hole. For example, in this picture, this blue cycle is maybe a good choice of holes, but this red one may be also good. So there can be many, actually exponentially many choices. So, and in this talk, we choose a representation called the harmonic representative of a hole. So this is a choice of vector in a so-called harmonic homology group HP. And this is defined like this. And this is also equivalent to the kernel of this p-dimensional combinatorial Laplacian. So yeah, I haven't talked about the inner product, but so this is this p-dimensional combinatorial Laplacian or Hodge Laplacian. The harmonic homology subgroup is equivalent to the kernel of this operator. And it is shown that the harmonic representative has a maximum contents about the bar. I think it is a reasonable choice of representation of a hole. Then the problem that we call harmonic persistence problem can be formally described like this.
Sorry, I didn't understand the previous this choice. So I mean, naively, if these, for example, these blue and the red lines, they do live in the kernel of the DP, and they live in the and they are in the complement. No,
they are not the vectors in a kernel of this space.
Are they not?
Yeah, they are not. So sorry. Yeah, I haven't given how the kernel actually, how the harmonic representative of this hole actually looks. But yeah.
Well, but naively they are, right? I mean, because DP acts on the like I can totally see myself acting with DP on this on either of these, right? So why are they not in this space?
Actually, so this combinatorial Laplacian is a sum of this term and this term, and this term is taking the boundary of the cycle. So if you apply the boundary to this blue cycle, this goes to 0.
Yes.
But if you apply this dagger of the p+1 boundary operator, this gives a upper dimensional objects, the triangles. So if you apply co-boundary operator, I call this co-boundary operator, and if you apply co-boundary operator to this line, this gives the sum of those triangles.
Yeah.
And if you apply the p+1 dimensional boundary operator, then so this does not give a 0. So
So it will give like the lines that are adjacent to the triangles that the first line is adjacent to.
yeah. So yeah, maybe the harmonic representative of this hole should look more complicated. And maybe I think they have to use all of those edges, but they can be written by using all of those edges. And yeah, of course, I can explicitly show.
So how there is no longer this redundancy you're saying? Okay.
Sorry.
There is no longer this redundancy. You say that the red and the blue are.
Yeah. For this.
Is it obvious from like the algebraic
Yeah.
nature of this? Because like I don't want to think about the D dagger. Like I want to just look at the it's in the kernel intersect with the complement of the image, and therefore there is no longer redundancy. How do I see that? How do I see that?
Yeah, maybe I don't really understand your question.
Like how do I see that this redundancy of choices is gone under this definition? How do I see that?
Okay, so if you look at this simplified complex, the dimension of this harmonic homology group is 1, and the vector in this group can be uniquely chosen up to the global.
I see. Yeah, that makes sense. Yes.
And this is a formal way of describing our problem. So you are given a harmonic dimension and the description of the three complexes. Each of them are given by graphs, graph adjacent matrices, and you are also given a succinct description of these elements in the harmonic homology group of the K1. So this must be a succinctly described. And the output is you have to put 1 if this all published in K2, and if we like it more formally, this you have to output 1 if this is satisfied, and you have to output 0 if this in this case. And the promise is either of those Boole conditions holds, and it is also promised that the minimum non-zero eigenvalue of the combinatorial Laplacian of K2 is inverse polynomially large. Then our result is that this harmonic persistence problem is BQP1 hard and contained in BQP. And this BQP1 means a perfect completeness version of BQP. So this implies, by assuming that BQP1 is not contained in BPP, there is an exponential quantum advantage for this harmonic persistence problem. And as I said, we have shown these results for Lie complexes, which is a practically relevant simplicial complex in PDA. So I think this result makes progress compared to the previous results on the normalized estimation problem of normalized persistence rate numbers. Okay, and I will give you some overview of the proof. So the containment in BQP is rather straightforward application of the quantum phase estimation. So I want to focus on the hardness side, and the BQP hardness is based on the reduction from a BQP1 compute. The first step of the proof is to prepare the initial simplicial complex K1. And we make this simplicial complex such that the n-dimensional n-dimensional Hilbert space can be encoded into the harmonics of this Greek complex. So this Greek complex K1 should have exponentially many some dimensional holes. And for the construction of K2, we start from some quantum circuit that outputs 1 with probability 1 if X is a yes instance, and that outputs 1 with no probability for the no case. And this quantum computing can be transformed into a set on 4 local projectors based on some variance of the circuit to Hamiltonian construction originally introduced by Kitae. And yeah, we can convert this quantum computing into a set of 4 local projectors. And then we can construct K2 according to the construction introduced in this paper. And the Q complex is constructed such that if X is a yes instance, the dimension of the harmonic homology group is larger than 1, and if no instance, it is 0. And we also need to pick a hole in this K1, and yeah, we can choose some vector in this harmonic homology group, and we have to show that this hole satisfies the desired properties according to the definitions I problem.
Sorry, like, so the BQP1 here is defined with respect to this gate set that you put there, like C0 on what is this other gate?
Yeah. So as you say, so for the perfect completeness results, there is a problem of choice of gate sets. So we specifically choose gate set for the C0 and some Pythagorean gate. It's called Pythagorean.
This is kind of particular, right? Because it's Pythagorean gate doesn't have any complex numbers in it. So it's like, you know what this U Pythagorean gate is, right?
Yeah, it is a 2-qubit gate, some specific 2-qubit gate, but sorry, I didn't write down.
Oh, okay.
But this is some universal case.
Result is somehow specific to this gate set.
For the hardness side, yes. And yeah, then okay. First, I will talk about the construction of K1. So K1 is a clique complex of this graph. So those star means some product or the joint product of graphs. So for example, if you have these two copies of this graph, the joint product of those graphs looks like this. So here, we are taking some all-to-all connection among those graphs. And if you construct a graph in this way, this clique complex satisfies something like this. So this is a whole chain space, and it is a harmonic homology subspace, and it is isomorphic to the n-qubit quantum space. And you can encode any n-qubit computational basis state into the some chain state in this 2n-1 dimensional space. And in order to construct the second simplicial complex, we want to construct such that it reflects the property of the 4 local set of projectors. So suppose that's a set of projectors is this, and we want to fill the holes that corresponds to the space that is penalized by those projectors. So this means I want to add some higher dimensional objects such that the boundary of those higher dimensional objects corresponds to the encoding of this penalized states. Then only the elements of encoding of the kernel of these projectors remains to be a whole. And in this paper, some general procedure for the set of Hamiltonians projectors for integer states is provided. So integer states is something like that, and they are the superposition of computational basis states such that the coefficients are all integers. Okay, so let me illustrate some examples. So the encoding of the zero state, single qubit zero state, can be corresponds to this cycle. So this is a superposition of 4 edges, and this is a harmonic of edges. And if you want to do something corresponds to this projector, you can just make triangle, add some vertex on the center, and connect to the center vertex to make the triangle such that this whole will no more be a hole. So this is a so simple example, but we want to do more complicated things. For example, consider this superposition 0 and 1. So this, if you encode this state into a simplicial chain space, this will become some entangled hole. So this may look like some of those cycles. So how can we fill this hole? Only this hole. So in order for this to the purpose, we first copy this cycle to this red cycle. And you can observe that there is some surgery is performed, and this connected part becomes disconnected, and so the copy of this hole appears as a red cycle. And then you can make some triangulated roof on top of the red cycle. So maybe you can imagine that if you wisely choose triangles and you take the boundary of the triangle, this 0+1 state appear as the boundary of those triangles. So this hole will no more be a hole by this construction. So I have said that the construction can be applied for any integer states. So maybe we can consider about this kind of trial state. So how do you do this? So the strategy is similar. So you can first copy this hole. So this construction can be decomposed. It is a combination of those two decompositions. So this zero hole is multiply copied in some multiplied way. And then you can similarly make some triangulated roofs such that this 2+1, 2, 0 plus get 1 appear as boundary. Okay. So okay, actually we have to consider more complicated things, but I hope those illustrations helps you understand. Okay, finally, the analysis of I will briefly mention about how we do analysis overall. So first, we modify the quantum circuit by adding some pre-idling steps, which means adding identity gates before performing quantum computing, and we can choose some subset state in a chain space as a harmonic representative of a whole. And we can give analysis of the overlap according to the using some techniques in the with the weighting with the construction of adding weights for vertices and analysis of spectral sequences.
Sorry, so this is something that's happening on the lower side, on the on this side of constructing the K2 complex, yes. But I thought that in the K2 complex, if you have a yes instance, then you just have some holes, and if in the noise you just have none, right? So somehow the trick was that you're saying, oh, you have no holes anyway, so of course it's not persistent, because it's not that any particular vector has not persisted, that no vector has persisted, right?
Yeah.
So why do you need to choose any harmonic representative in that case?
Yes, that is basically in order to make the program contain the DQP.
Oh, okay.
Because
Also, this is not for
yeah.
BQP, you're not talking about
Yeah.
BQP hardness right now, you're talking about BQ containment. Okay.
Yes, so yeah, I am saying that the BQP1 hard instance can be encoded in the some promise problem.
Oh, you're talking about, okay.
Yeah.
So you're trying to ensure some promise. What promise you want? You want to ensure that the gap that the gap of the operator is
Yeah, in the overlap.
Oh, okay.
Those properties must be satisfied.
But what does this have to do with choosing a representative? I thought you just need to show the spectral gap of the harmonic operator. Why do you care about the sigma?
Because so finding such a state, such a
There was some other promise
Because you're given a description of a hole's input as well, right?
Oh, you need to be
Yeah,
given.
yeah,
Oh, yeah. You
yeah,
just.
yeah.
Oh, that's just. Oh, that's the promise. Okay, got it.
yeah,
As far as input.
Yeah. True. Yeah.
Check it per specific.
That was for the K1. You have to say, but the way you constructed the BQP1 hard instance, that there was no. Was there? Yes. Yes. So you were just talking about constructing the sigma for K1, then not for K2, because for K2,
sigma is for the sigma is the harmonics.
no, for
On K1 and sigma not necessarily be the may not be the harmonics of K2.
yes.
Because even if the whole persists, the harmonics will change in.
No, I understand, but like, why do you need to have sigma description of K2 because if sigma may not belong to HP.
Yeah, it is not a description of harmonics in K2.
Yes.
It's just a representation of some vector in the harmonics.
So going back to the BQP1 hard construction, yes. So you were trying to construct a sigma for a complex coming from this the K2 complex, right? Because in K1 you just have sort of all vector and sigma.
Yeah, many ports. So
you just have everything. So you just pick something. So now you're trying to construct sigma that somehow had to do with quantum circuits. So I don't understand why do you need to do this? Because if you just pick some sigma from HP of K1, then okay, you're sort of you're done. You could have picked like a zero state or something. You don't care.
Yeah.
And you don't care. I mean, it may or may not be.
Yeah. So maybe this is some artificial construction of problem instance such that if X is a yes instance, this sigma have a large overlap in
Needs to be there. Yeah, that's right. Yeah. Okay, got it.
And you want it for the specific sigma.
Yeah. No, sure. It's not just So it's not enough to show that this that it has multiple. It has some holes. The K2 sigma needs to be in there specific. Oh yeah. Good. Beautiful. Thank you.
Okay, maybe I will click search. And we have considered other formulations in the paper as well. So I have talked about this harmonic persistence problem, but so this is based on the pair of simplices, but we can also show some problem that is for a single simplicial complex that have a similar complexity. And we have also considered in this problem we use combinatorial Laplacian, but what happens for more general sparse Hamiltonians? And we call such a problem as kernel overlap problem. And these are the similar complexity. And if we generalize this kernel to some low energy overlap problem, it will become lower. So we also study those kind of problems. And as a future directions, our results only shown to be hold for weighted three complexes, but we conjecture that this similar result may hold for the unweighted three complexes. So can we show this? And there is an interesting operator considered in topological data analysis called the persistent Laplacian operator. So this is some operator that knows about the persistence, but this is an operator that maps to this Ci P to CIP. So this is maps from initial simplification complex to initial simplification complex. So we have so far we have the combinatorial Laplacian. Yes, about
So is there a typo? It has to be a J and when you delta J.
No, this is true.
Oh, okay.
Yeah, so this PJ delta PJ maps this J to J, and this I maps I to I, but this IJ maps I to I, but this operator contains information about the persistence. So yeah, so this is an interesting operator. So can we show similar complexity results for this guiding version of persistent Laplacian problem? Okay. So yeah, this is the end of my talk, and I found this in some museum. so this is maybe in Delfto, and I think this connects many complicated holes in a matrix. So I think you have studied that kind of policy problem for a long time. Thank you for listening.